This video is about using algebra and graphing devices to solve polynomial equations. It's just going to be a culmination of many theorems and definitions regarding polynomial functions. And so, in fact, for the notes, we're simply going to say recall all theorems and definitions of polynomial functions. Let's consider the example that follows. We want to find all zeros. All means all. They may or may not be rational. We want all zeros of the polynomial function. We want to use a graphing calculator to find the first root, then use the factor theorem to find remaining roots. In other words, we're going to just cheat a little bit or get a nudge here in the right direction with the graphing calculator. The rest of it will follow from all of our theorems. To get going with our calculator and get started with our first root, we'll go ahead and type our function, polynomial function, in our y1 equation slot. And so you can see I have it typed in here just as it's read. And then we want to find our first zero with the help of this calculator. We've seen this before in other contexts. We can hit second and then the trace button, which is the calc menu. And you'll notice the second option says 0. That's what we want. We want to find a 0. We hit enter in that option. It takes us back to a graph window where we can see a graph of our function. And we need to be able to spot visually 1, 0 to use. And you can see maybe a couple options here. I'm going to pick on the one that looks like it's close to -1, or maybe, I'm sorry, -2 in the x-axis. It might be -2, but we'll find out for sure when we actually go ahead and go through this function here of 0. The first question asks left bound, so we scroll with the left arrow until our cursor is clearly to the left of where that 0 is, and hit enter. Then we want a right bound, so we'll go ahead and back up past the 0 to the right clearly, hit enter. Then it wants a guess, so just go back close to where the axis is. It won't possibly hit right on the axis with the cursor, but close to it, hit enter. Let it think for a moment, and it spits out the value -2 for x and 0 for y. So sure enough, it hit it right on -2, 0. That's right at the x-intercept. So we can say, thanks to our calculator, that c equals -2. Remember, c is just a variable used to represent a root, and so we found that the calculator told us -2 is one such root. Now, we have many more roots to find, and before we take off running on this, let's observe how useful some of these theorems will end up becoming. First of all, if we had a simple quadratic equation, often we can just factor it to find the roots easily. Or maybe not easily, but at least possibly in that way. But notice our polynomial has 1, 2, 3, 4, 5 terms. There's really no good way to factor a polynomial in this form unless we leverage and utilize the factoring theorems that work for polynomials. And so we'll start with our root of -2 and then use synthetic division where we're dividing by x minus c, where in this case c is -2. We want to use the synthetic division process, which would mean we're going to write our coefficients out from the original polynomial in order. Notice we're not missing any powers of x. They're all in order, so we'll just write them out as 2, 15, 31, 20, and 4, the coefficients of our polynomial. We'll leave a space underneath all of those, and then drop the first coefficient down, the 2, and then it all just kind of falls out from here. We'll go -2, our c value, times 2 is -4. We write that up above the 15. Then we add down vertically to get 11. And repeat, -2 times 11 would be -22. Add down vertically, and that should give us +9. -2 times 9 would be -18. Add vertically, that gives us a +2. And then -2 times that 2 is a -4. Add vertically in our last column to get 0. Now remember, we better get 0 there, right? If -2 is a root, as we've seen in the calculator, then our polynomial theorems would indicate that we better get a remainder of 0 when dividing by the root that we have here, -2, and we do. What this can tell us is that we could now rewrite our polynomial, which we'll do, p of x equals, but we're going to use the root we just found and write it as a factor of the polynomial. X plus 2 would be a factor of our polynomial. Notice the opposite of the sign that we're seeing in the c value there. That's because x minus c is what's in this root, but that's really x minus -2. So we have a +2 inside the factor that's representing this polynomial. But then after that factor, we have to put what we got in our synthetic division process before the remainder. We use these numbers simply as the coefficients. So we'll write this as 2x cubed. Remember, we're doing 1 degree less than the original. So 2x cubed plus 11x squared plus 9x plus 2. What we have now is that we've factored our polynomial, but we still have a binomial times a 4-term polynomial, and that's still a little large for our liking, which means we're going to restart or redo this process, repeat it, but now try to split up this 4-termer. And again, we'll start by using a graphing calculator just to give us a little hint on the root before we go ahead and use the synthetic division to go from there. If we go ahead and type the 4-term factor we have currently going in our polynomial into our graphing calculator, again, that's 2x cubed plus 11x squared plus 9x plus 2. We want to try to find a root of this one now so we can start to split it up using our factoring theorems. We can again try to use the calculator to give us a little nudge here, and if we do so by zoom 4 just to kind of center out the window and get a good picture of the graph, you can already spot that it looks like there are probably a couple different roots. We see one close to the origin here we might want to utilize. So let's go ahead and hit the second and then trace button. And then we want to use option 2, which says 0. It'll take us back to the graph, asking for a left bound. So we scroll left until our cursor passes where that place is. Looks like it's roughly -0.5 or somewhere like that. We'll hit enter to the left of it. Now it wants a right bound. We'll go back to the right, hit enter again. And then it wants a guess, so maybe go down to as close to the bottom as you can. Hit enter, and it's going to spit out a value. Now the 0 it's giving to us looks a little interesting. It looks like it's having to round a decimal here. The x-coordinate it says is -0.4384472, and then it gives us a y value of 0. So it's trying to find a 0 here, but I'm a little suspicious of this x-coordinate. Now the reason is because, first of all, the calculator is estimating. Sometimes it's good enough to get it right on, and sometimes it's not quite. The reason we might be suspicious of this x-coordinate here for the 0 is that if you look back at our polynomial function and then apply some of our theorems to it, you'll recall that the theorem of rational zeros says that all the factors of the constant term, which are 2, the integer factors that is, so we have plus or minus 2 and plus or minus 1. The factors of the leading coefficient, this would be like the q's, would be same thing, plus or minus 2 and plus or minus 1. Putting all these together in combination would give us an option that seems to fit close to what the graphing calculator was saying. Remember, it was like -0.4 something, but one option out of all these combinations, as we saw when doing the theorem of rational zeros, would be that -1/2 is a possible root, a rational root that is. So that might be the one we need to utilize for this. We'll have to test it out. Of course, we'll know very quickly if it's going to work or not, because when we do synthetic division with it, we're either going to get a remainder of 0 or not. Let's go ahead and give the synthetic division a whirl here. We're assuming that -1/2 is possibly one of our roots. Let's go ahead and verify that -1/2 is a 0, and we'll do so by doing synthetic division, where c is -1/2. All right, so we'll start by dropping the first 2, the coefficient, right? These 4 numbers going across after the c value here, these are the coefficients from the 4-term polynomial that we're trying to factor and split up here. So we got 2, 11, 9, and 2. If we go through synthetic division, we'll drop the 2 down. -1/2 times 2 would be -1. Add down vertically and get 10. -1/2 times 10 would be -5. Add vertically and get 4. -1/2 times 4 would be -2. Add vertically and get 0. And what do you know? That means, according to our theorems, that -1/2 is indeed a root of, again, we're talking about this 4-term factor we had just at our previous step. Furthermore, the three numbers before that zero remainder will give us the coefficients for how to split up that four-term factor. In other words, now we can say that p of x, our original polynomial, is what we had previously. There was already a factor of x plus 2 that was known. But then everything after it we just split up. In fact, we split it up with 1/2 as a known root. We found that. A little bit of help with the calculator, but not much. So we could say x plus 1/2. And then after it, we'll now use the three values shown in our synthetic division process, which would tell us 2x squared plus 10x plus 4, right? So this is 1 degree less than the degree of the factor we just split up, which was degree 3. And now we're just using these coefficients in their order, 2, 10, and 4, which means we're getting there. Now we're left to a couple binomial factors, but then a trinomial. But a trinomial factor, especially one that's quadratic like this, could be factored possibly either using a factoring method for a three-term trinomial, or if that doesn't work, we might have to try something else. Let's go ahead and see if we can get it that way. So we'll say p of x equals x plus 2 times x plus 1/2. And then you could take a 2 out of all these, common factor of 2. If I rewrite it that way, that's really x squared plus 5x plus 2. And then you can try to think through maybe some guess and check, but it does not look like that's going to work, given any factoring method we have. So if it's not factorable, that means we still could use the quadratic equation or the quadratic formula on this. Let's go ahead and try to do that to see what happens. If we try the quadratic, well, first of all, let's just say here, we're sad because this is not factorable. But we'll try the quadratic formula to come up with some roots for that one. So we'll say x equals negative b, which is 5, plus or minus the square root of b squared, that's 25, minus 4 times a times c, that'd be minus 8, and that's all over 2 times a, which would be 2. So indeed, this will work out as some roots or zeros, but they're not rational, right? This would be just negative 5 plus or minus the square root of 17 all over 2, and that's not reducible. So that's fine. It's still part of our answer, but notice it's just not a rational zero. So all of our zeros at this point, given everything we've done, would include negative 2 coming from the first factor, negative 1/2 coming from the second factor, and then the solutions of our quadratic formula attempt here, which would be negative 5 plus or minus square root of 17 all over 2. So that's a total of 4 zeros, but 2 of them are irrational, which means that's why you can see them there with the root, and we had to use the quadratic formula to find them.